So as a final topic of today's lecture, we're gonna consider stress concentration in structure. So the question I want to ask by opening this video is that, like, in the presence of a hole or a crack, like, where does the failure initiate? Okay, or if you are like listening to this video, please stop the video and try to prepare a paper and make a hole in the center and try to tear the paper. Okay, so what you're gonna find is that you always see the failure initiate from the tip of this crack or hole. Okay, so out of like many different cross sections, you always see crack propagation and failure initiation at cross section 1 instead of 2, which does not contain crack, and there is a reason why. Okay, and the reason is stress concentration. Let's first consider one case. Suppose that you have this sample under tension force P. Okay, and yeah, I didn't draw this detailed enough, but you have a hole for entire section. Okay, and under the force P, the height is D, and the width is thickness is T, and the radius of this hole is R. Okay, so if I draw only side view, you have a hole with diameter 2R. Okay, and you are trying to make a tension for this sample. Okay, so what people have found is that stress distribution around this point and that point will be almost uniform. Okay, almost uniform. However, stress distribution near the hole is not uniform. Like you're gonna have a huge stress near the near the defect, and the stress decreases quite rapidly like this. Okay, so for this problem, if you consider the ratio between maximum stress here and the average stress, to obtain average stress, you have to consider this plane. This plane have the I would say average, the thickness is T, but height is D. This is D minus 2R. So the effectively that these two planes, this area and this area, this cross section has the overall the area of T times D minus 2R. Okay, then average stress within this gray zone is given as P over T times D minus 2R, and we call K as a stress concentration factor that relates this average stress and the maximum stress here. This is the maximum stress. Okay, so it's quite interesting when R is much smaller than D, the height of the sample. Actually we can solve this by by solving partial differential equation, and we can get analytical solution. And actually we can we found that the K is exactly 3. Okay, however, if the R becomes larger and larger, this is the case when R is much smaller than D, such that R over D approaches 0 and K is 3. However, when R gets larger, stress in concentration factor becomes smaller and smaller, and you can find this figure out of page 118 of 7th edition of our textbook. Okay, so if somebody gives you the dimension of R and dimension of D, you can obtain the stress concentration factor out of the table. If you have a computer, you can get this solution from computer simulation. But as an undergraduate, you don't have access to computer simulation of solid mechanics code, so you can only rely on the table offered from your textbook. And if you look at textbook and look at the dimension of R and D, you can find the stress concentration factor that connects maximum stress and the average stress within the cross section. Okay, so this is the stress concentration factor you have to consider when designing joint and connections. And second case is when you have like a wide section here, and like a less wide section, a shallow section here, like a large d and small d have a different value, you're gonna have a stress concentration here. Like you're gonna have a higher stress here, you're gonna have a small stress here. Okay, and uh, and you can of course make a relationship between this maximum stress, this is maximum stress, and the average stress over the entire cross section, and K is the stress concentration factor connecting these two, and you can find this stress concentration factor as a function of R over D when this radius R and D ratio, and when the ratio between large D and small d as a function of large D and small d ratio as a function of R and small d ratio, you can obtain stress concentration factor. Okay, so the implication here is when R is very small, you're gonna see very high K. When D over D, this ratio increases, you're gonna have higher stress concentration factor. Okay, as R goes to 0, K becomes infinity. However, in real world, R cannot become 0 because material is made out of atoms. Even though you make a one atom sharpness, each atom can have a finite radius. You cannot have infinite stress concentration factor. Of course, in mathematical world, if you assume and imagine like complete ideal continuum world, you can have exactly zero radius curvature at the corner, and you can have infinite stress concentration factor K. Okay, so one of the engineering application is like when you imagine like a Apple charging cable, try to look at your Apple charging cable. You can see that it will have very small radius curvature here. And what does it mean? Because it has really small radius curvature, there are going to be huge stress concentration, which means that like if you use your Apple charging cable or Samsung charging cable quite a long time, there are gonna be some problem in connection here, and the electric wire here will fail eventually, and you have to buy new charging cable. Okay, so this is quite interesting engineering application of using stress concentration, which forces you to replace your charging cable quite often. Okay, but I'm not sure whether they do the design in that purpose or not, but it's quite interesting to see like a Apple charging cable in that way. Okay, so anyway, so regarding this table, you have to also refer page 118 to get value of K, which gives you stress concentration factor as a function of large d, and small r. Okay, and based on that stress concentration factor table, you can solve some example problem. Okay, so the message I want to deliver is we have to consider stress concentration, especially when designing joints and connections. Okay, so the example we're gonna solve is we're gonna have a structure with large D of 60 millimeter here, small d 40 millimeter here, and the radius curvature is 8 millimeter at the joint, okay, at this corner, and the thickness is 10 millimeter, and given the allowable stress is 165 megapascal, what will be the maximum tensile force we can give to that structure? Okay, so from this ratio, large D over small d, and from R and small d ratio, we can find and identify K equal 1.82 from page 118 of 7th edition of your textbook. Okay, now you have to make a connection between maximum stress and average stress, and the maximum stress must be smaller than allowable stress. Okay, so if you obtain the and this is the safety designing criteria you have to use. Okay, so please note that in chapter 1 we haven't done that. Okay, but anyway, let's forget about it for now. And if you plug in sigma max equals to be K times sigma average, and this must be smaller than allowable stress, which is 165 megapascal, and the average stress must be 165 divided by K, which is 1.82, is given as 90.7 MPa. You can see that you gotta be really careful about designing joint. You thought you can have average stress around 165, but due to the stress concentration factor, because stress magnifies near those sharp corners, you have only this much of freedom. Okay, so the average stress must be P over 40 millimeter multiplied by 10 millimeter. So P should be smaller than 36.3 kilonewton. Okay, so this is really interesting, right? By considering stress concentration factor, you lose huge buffer. Okay, and the implication is our analysis on joints in chapter 1 was wrong, right? When we consider like road BC, and which is under tension acting force here, and we worried about like safety of here, and we compare the stress analysis stress at these point and the allowable stress, but at that time we didn't consider the stress concentration factor. Okay, so our analysis was completely wrong when designing the joint, and after learning this kind of new knowledge, the stress concentration factor, we are now learning new things, right? So when designing joints, it's not only matter of smaller cross section. Like when designing joint, in addition to smaller cross section, you have to worry about stress concentration when the structure have this sharp holes and sharp corners. Okay, this is feature for like a most partial differential equation governing natural world. Okay, the stress field in solid mechanics and electrostatic field in electromagnetism, they follow similar partial differential equation. And I think I told you in the first lecture in ME231. Okay, so when you have a very sharp tip at the top of the building, you're gonna have your lightning on the tip of that node. Okay, the reason is there is electric field concentration. The same and similar mathematical phenomenon occurs here. When you have a sharp hole, when you have a sharp corner, you're gonna have a stress concentration, and stress concentration must be taken into account when designing structural safe design. Okay, so with that, let me finish the video here, and with this I can finalize today's lecture.